This set of videos is going to be split into a calc part and a pre-calc part. So we're going to do the calculus part. We're going to keep talking about the derivative, and we're going to talk about graphing the derivative. So in our last set of videos, we saw that the derivative is just its own function, right? We had f of x, and then using our limit definition, we found f prime of x. So it's its own function, and any function can be graphed. But there's going to be some relationship between our function and our derivatives. All right, so we can use the original function to help us graph the derivative, because we know the derivative is the slope of tangent lines. So let's say we had this function, and we're going to graph its derivative. I'm going to graph it on the same axes. What we need to do for each x value, we need to figure out what is the slope of the tangent line. So we can start over here at 1, 2, 3, 4, -5. At -5, we look at the tangent line there, and because it's flat, the tangent line's 0. So on my derivative graph, I'm going to get 0. At 4, it's the same thing, it's just this flat graph. I get tangent line 0. At -3, 0, -2, 0. And then 1 is the first place where something interesting kind of happens. We have this sharp corner right there, and we know the derivative doesn't exist when there's no sharp corner, so that part of our derivative function is not going to exist. All right, at 0, the tangent line is just going this direction. It looks like it's up to over 1, so it's up to over 1 means 2 is the value of the derivative. And then everywhere after that, here at +1, again, we have a sharp corner, so it's not going to exist there. At 2, it's a flat line, so the slope is 0, and that's going to continue this way. All right, so everywhere that we have these flat lines, I can kind of connect, because the derivative is 0 everywhere for any of those x values. I don't just have to do whole numbers, but the numbers in between. Anywhere on this slanted piece, right, is going to have a slope of 2. All right, so that's going to be up here. And then at 1, it doesn't exist, so I'd have to put in these open circles at the end of each one of those. So there's a lot of writing on there. So the derivative ends up looking like this, the derivative graph. All right, 0 for all the numbers that are on the flat parts of the line, and it's 2 for all the ones on that slight diagonal. And then at 1, it doesn't exist because of the sharp corner, the cusp. All right, so I can go from the graph to my derivatives graphs. All right, just to make it a little bit cleaner on this one, I am not going to graph it on the same axis. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8. And let's just go up. All right, so I already made one mistake by making the axis like this, assuming that the axis for the graph is going to be the same as the axis for the derivatives, so I'm also going to have to extend this downward. But yeah, let's just kind of start off with the whole numbers first, and we'll figure out what's going to happen in between the whole numbers. We mentioned before, at 1, we have this peak here, so right at the top of the peak, my tangent line ends up being flat. All right, so that's going to give me 0 for the derivative at 1. At 2, my tangent line is going to be going in this direction. Again, we're guesstimating a bit. It looks like it would be about down 2 over 1, and that's -2. At 3, the tangent line would be flat again, so we're back to 0. At 4, our tangent line is going this direction. It's a little bit steeper than it was at 2, so maybe it's up 3 over 1, so the slope of that tangent line seems to be about 3. At 5, it's going to be flat again at the top there, so at 5, it's 0. At 6, it looks really similar to what it looked like at 2, so I'll also say that one is -2. At 7, it's flat again because it's making that turn. So at 7, it's also 0. And then at 8, it's going up pretty quickly at 8, so let's just say it's the same as it was at 4. Let's say it's 3. All right, so when our tangent line is going upward, we should have a positive one. And when it's going downward, we should have a negative slope. I didn't even start at 0. 0, it's going upward as well. So maybe at 0, we could also say maybe it's not as steep as at 4. So let's just say it's like 2. And then all of this part of my graph, all those tangent lines are going to be positive. So I should always have positive values for my derivative. Once I hit that peak there, I turn, and now all these ones are going downward, so all my derivatives should be negative until I get to 3. Then it'll all be positive going up until I get back to 5. Then it's always going down until I get back to 7, and then it's going up forever after that. All right, so this is the slope of my derivative of that function to the left. And again, you can see a couple relationships. Anytime my graph is going in the upward direction, which are these kind of ones I'm highlighting right now, my derivative is above the x-axis. And then anytime my graph is going in the downward direction, like these 2 seconds, my derivative is below the x-axis. And then in the middle of those are the flat pieces. Those are where my derivatives exactly equal 0. All right, so you can see this relationship between the graph of the original graph and the graph of the derivative. Now, one thing students try to over connect is like intercepts on the derivative to intercepts on the original graph, but an intercept on the derivative just means that the original function has some type of flat tangent line, and an intercept on the original graph means nothing in the derivative. I could have a bunch of intercepts on the left, but like none on the right. Right? The intercepts don't kind of line up the way you might think. Right? But just looking at the original graph, thinking about when the tangent lines are going up and when they're going down can help you get the graph of the derivative. And we're actually going to do this in class to help us figure out the derivatives of a couple popular functions, right? Ones we haven't really talked about a lot yet. But if we kind of just look at the graph of the function we care about, think about all the tangent lines, we can find the graph of the derivative and see what the answer's going to be.